Hi Karthik. Hi all. Thanks for joining the call. Okay, let's start today's call. I started the recording. Okay, let me share my screen. Okay, so yeah, you can see my screen, right?
Yes,
Yeah.
yes.
Okay, okay. So hope you guys have gone through this document yesterday. Do you have any doubts, any questions? I mean, not this till this at least HDFS part. What is name node? What is data node? Standby name node, secondary name node, those kind of things. Do you guys have any doubts so far?
No doubts there.
No doubts.
Mm,
Okay.
no,
No. Okay. That means you are able to understand, right? Okay. Okay.
Yes.
So in today's class, yesterday we already saw some example, right? How this map reduce is worked, right? How mapping is done, how reducing is done with some good example, right? Yesterday, good, bad, average. So that was example we used yesterday. And we were able to see how map reduce happens in the right. Now let's see the technical part of it. Like in the yesterday, you just saw like how just normal common example, but in the real now we will start to see some technical part of it. Okay, so let's start from here. Okay, MapReduce is a program. What is MapReduce, by the way? What is MapReduce?
Uh, MapReduce is a program framework
Okay.
uh, that allows distributed parallel processing on large datasets in a distributed
I mean, this
Same
is the
here.
definition we gave here, but I do not, I never want you to explain the same definition. Actually, I want you to give me the definition in normal words. Let's say
Okay.
MapReduce is a processing component of Hadoop environment. It performs, let's say it's a programming framework, okay, or software framework, okay, or and it will allow us to perform some distributed and parallel processing on large data sets. That's it. That's the definition I want to hear from you, not the exact definition. You can never remember this exact definition. Okay, just try to remember what it does. MapReduce is a programming framework for sure. MapReduce is the processing component for Hadoop for sure. It will do distributed and parallel processing on large data sets. That's it. Okay, just try to keep it as simple as that. Never try to remember this kind of definitions. Okay, just for explanation part we will put it here, but yeah, just never try to. Okay. Yeah, that's good. Now let's start. What is MapReduce? As we already know, MapReduce means map and reduce, two separate components, two separate concepts. Okay, one is mapper and another one is reducer, right? Mapper phase and reducer phase. Yesterday we saw that, right? Mapper phase and reduce phase. As the name map reduce suggests, see, reducer phase takes place after the mapper phase has been completed. We already know this, right? Because without mapping, you cannot reduce. Without even starting your job, without even mapping your data, you can't even start. Fine. Now, so the first is the map job. Okay, so definitely first should be the map job. Okay, then where a block of data is read and processed to produce key value pairs. Yesterday we saw how key value pairs are produced, right? Good comma one, bad comma one, average comma, so like that. We just mapped it and we just created a key value pairs. Now these key value pairs, we again reduced it. Right? These key value pairs are input to a reducer. That output of this mapper phase is input to reducer phase for sure, right? Because this output is an intermediate result, it's not the final result, it's just part of that result. After this output, we will calculate, we will add, we will do some more functions like okay, so all the good related data should be in one reduce, now all the bad related data should be in one reducer, and this average data should be in one reducer, right? Then we can start calculating. Now we will start calculating the data. Fine. See, you got the input and you split that input and you done the mapping, map 1, map 2, map 3. First this mapper task will run. Fine. Then you will have a shuffle shot here. Yesterday we saw what is shuffle shot, how it will happen, and then it is go and sit into this reducer. Okay, this reduce it's also a kind of data node. Now you can have multiple reducers or you can have the single reducer as well. Then this will be shown as a output to the end user or the client, we call it as. Okay, that's what we saw yesterday. And you see the output of a mapper or map job is input to the reducer for sure, right? Yesterday we saw that. And the reducer receives key value pair from the multiple map jobs. We saw that, right, yesterday. Using the shuffle shot, you used to get that input output to, we used to send that output to as an input to this reducer job. Yes. Then the reducer aggregates those intermediate data tuples. Data tuples you saw, right? Key value pair. Key value pair. So if data tuple is like braces open, that key name comma one and braces close is a key value pair. Intermediate data tuples into a smaller set of tuples or key value pairs, which is the final output. You saw, right, yesterday? I think I'm not sharing the screen. Let me stop and reshare. Okay. So actually, this is what we saw, right? This is the input. Okay. This input is split into three blocks. Okay. This input is split into three blocks. And if you remember, it was done very intelligently, right? It could have done like this: good comma, BA and D. No, it hasn't done that. It done it very intelligently, very logically, right? As per the logic, good should be one word, good should be one word, and bad should be one word. And it shouldn't do this BA into one output and one split and D into one split, right? It never did that. It just did it very intelligently. It input split the three blocks. Okay. Then this is mapped. Here the mapping has happened. Okay. The mapping has happened, and now this mapping is like we just calculated the results at this block only. That means we just calculated how many goods are there in this block itself, and good two, bad one, and same here and same here. Now with the help of shuffle shot, these are the reducers, as we already know. It could be two reducers or could be one reducer. These are the reducers. So to the reducer, we just gave this data, and reducer calculated the data and just gave the final output here. Right? This is how it looks like. Okay. Any doubts in this yesterday's example? Fine, right? How we calculated this map reduce program, how we written this map reduce, this flow algorithm or whatever we call it, entire flow of this map reduce program. No doubts, right? Or any doubts? Just let me know.
No
Yeah.
doubts, sir.
Okay. Cool. Similarly, let's see this example. Okay. Fish swims in the sea. Big fish eats small fish. Red Sea has pet fish. Before, this is input chunk. Actually, this belongs to one file only. But we done some splitting, input splitting. Okay, we done some input splitting. Then it becomes three blocks to us. because name node knows, right? Whenever there is a file, it will try to create a blocks. So let's say this is block 1, block 2, block 3. But here I do not want to use the term block. I want to use the term called split, input split. Okay, you will let you know. I will let you know what is the difference between input split and block. Because in case of block, right, it's a physical representation of the data in the physical location. Okay, but in case of this input split, right, it never have the physical location. It's just logical splitting. Okay, you will get to know the difference. Okay, just it's a imaginary. In the real time. This name node remembers everything, entire thing, and it will just remember this thing. It won't store this data anywhere. This is not the physical location. This is for just processing. It just splitting in this way. But in the real time, the block is a different. It's a physical storage. Okay, you'll get to know. There is a one slide here where we can explain about input and block. Okay. Yeah, now this input split happen. Okay, input split is happen. Now we just need to map. How we are going to map? Key value pairs, right? This is key, this is value. For this key, this is the value. Swims 1, in 1, d1. Similarly, as how we did it yesterday, right? Again, this map. Okay, now fine. So now we need to do some shuffle shot. Why? Because as we are up to calculating number of occurrences frequency of a word, so we need to do some shuffle shot so that all the keys will go into one reducer, right? Either of the reducer, all the keys will go into similar keys will go into the one reducer. Then we can do local aggregation. In the local here itself, we can start doing this. So fish in total it's four, has one, big one, it's one. Okay, in one red two, C2 again, and small one swims one, D1. Right. This is how we reduce the output. Now we will display this output to the user. Okay. Now let's say advantages of MapReduce. Okay. What is the advantage of MapReduce? Parallel processing. See, here we are doing this in parallel, right? This input split 1, input split 2, input split 3. We are doing this processing in the parallel way, not the one by one, right? I never yesterday. If you see here when I constructed this, maybe I just draw one by one, but in the real time, this once this is done, this is a separate node, right? This is a mission, and this is a mission, and this will be processed by a mission. So they will do this processing in the parallel way. It will never do that. Okay, after this block completed, I will do this, then it will do this. No, it's not the same mission that is processing these three blocks, these three splits. It's the different missions, three different missions processing this. Okay, three different missions processing the data. Oh, okay, three different missions processing the data. That's why it's in parallel. Okay, it's parallel processing is how it looks like, right? Parallel processing in MapReduce we are dividing the job among multiple nodes, right? We have seen that multiple nodes, each input split will be processed by the each different node. That means each task, let's call that as a task per node. That task is provided by different nodes. Okay, different nodes. Okay, and yesterday, day before yesterday or something, I told you a concept called how my laptop has CPU cores of 4. Then how many executions my laptop can do in parallel? Can anyone let me know that? My laptop has 4 CPU cores. How many parallel executions can my laptop perform? Parallel task running, parallel processing, whatever we call parallel tasks. How many executions? How many can my laptop do? Any guesses?
Three, sir.
Sorry,
Three.
3. No, my laptop has 4 CPU cores.
It's 4
4. Why?
because all the data sets will split
It will split, and
into
as
4.
as my system has capacity to run only 4 tasks in parallel. Only 4 tasks
Yes,
in parallel. It depends on my CPU cores. Let's say if I have 16 CPU cores, how many parallel processing can my computer do?
16.
16.
16.
16. Yeah, 16. Okay. If my the number of parallel tasks is equal to number of tasks in a number of CPU cores in a laptop, in a mission, in a node, in a system, whatever we call, in a commodity hardware. Commodity hardware means generally used hardware. That means laptop is a commodity hardware, phone is a commodity hardware, desktop is a commodity hardware. So those, all this comes under commodity hardwares. Okay. Okay, so far clear. So that's how this parallel processing is happening. MapReduce, we are dividing the job among multiple nodes, right? We are dividing the job. How we are dividing? We take the input, and that input is split into multiple blocks or multiple splits. Okay, then it was spread among multiple nodes, because you saw, right, multiple nodes. Um, what happened? Yeah, multiple nodes. This is node 1, this is node 2, this is node 3. Multiple nodes. Okay, and each node works with a part of the job simultaneously. Part of the job. It's not the entire block, entire split that these nodes are processing. They are processing just part of the input data, right? It's not working on entire data. And so MapReduce is based on divide and conquer paradigm. That means like rule, or we can say paradigm means rule. Okay, based on divide and conquer, right? How we are doing it? We are doing in divide and conquer, right? So this good, we divided this into first split. This entire input we divided into splits. Okay, divided, then again divided. Then here we just started like conquering in the sense we just started combining the values. Here also we started combine. Here we combine, and finally we combine it one more time, right? That's how we do. And and okay, now divide and conquer paradigm will help us to process the data using different machines very quickly, right? Because this divide, right, we are giving some part of our input to each missions, and each missions will process that small input as per the logic given to them, program given to them. Because we need to instruct the machine, right? My laptop can do any processing, but you need to tell what it needs to do, right? We will give some logic to them, program to them, and it will start processing. Fine, super. Now, still clear, right? Parallel processing. What is parallel processing? You clear, right? These lines are self-explanatory. Even though self-explanatory, I'm just trying to explain you just with the example. Yeah. Someone want to say something?
No, no, sir, no.
Okay, fine, super. Now data locality. Instead of moving data to the processing unit, okay, data to the processing unit. Catch, there is a catch. Because we are we are this is a data node, and we are sending our data to this data node, right? Not this data to the processing unit. Let's say you know rice mill, right? Rice mill, rice flour or something, right? You used to go to that mission, right? There is some machinery, set of machinery. You used to take your rice to that machinery, and they will start grinding that thing, right? And then they will give you the output. Right? You guys aware of that rice mill?
Yes, yes.
Right? What you are doing, there are processing units installed it somewhere, right? You used to take your rice to them, and they used to process that rice, and they used to give that output, that the flour we call it as, right? Flour, rice flour we call it as. Then you used to take this, and you used to prepare those or idlis, whatever you want, right? That's how you used to do. Similar, but in this case we are not doing that, right? We are sending our data. I mean, we are sending that processing unit. What if, see, in the real time, the processing unit are installed somewhere. I mean, in this example, you used to take your data, I mean data in the sense rice, and just get it grinded there, right? But what if there are small rice machines, grinders, right? The grinders will come to your home. If you book them, they will come to your home, and they will cook, they will grind the rice for you, and then they will leave. That's it, right? So that's how this data locality works. Instead of moving data to the processing unit, instead of moving your rice to the rice mill, we are moving the processing unit to the data in the MapReduce framework. Right? Remember this small example. Maybe I just wanted to give you this example so that you guys will understand better. Okay, remember this. Instead of going to your rice mill, you can use your this grinder as well, right? To create some flour. Or maybe you think of a rice mill, right? I'm thinking of these machines where set of machines will be there, and you take different kinds of ingredients, and they will mix it. They will grind it and give that output to you, right? Instead of taking this wheat, paddy, or whatever that. But yeah, that's a small example. Okay, right? In the traditional system, we used to bring data to the processing unit and process it in the traditional system. So you will install your processing server somewhere, and data is lying in somewhere. You will take the data and give it to the processing layer. It's kind of a like mission, some mission. It will take your data, what we call that, in airports you will put your bag there, then that machine will take that bag forward, right? Something we call it a submission. So like that, we are not going to put our data in like that. Okay, so we need to take that processing unit, okay, and then process our data. That's what data locality means. Instead of moving data to the processing unit, we will take that processing unit and we will process our data. In traditional system, that's how it happens. You used to send the data. I think it's called lay or built or something. So it's keep on moving. It's keep on moving. You will put your data there. It will keep on moving, right? Then it will take the data to there and it will start processing it. Okay. Now, but as the data grew and became very huge, bringing this huge amount of data to the processing unit posed the following issues. As the data grew in the real world, right, that's what big data problem is. Data is very huge. Data is very fast, velocity. We discussed the 5 V's, right? Then this moving huge data to processing is costly, definitely costly, right? And deteriorates the network performance because it entire data needs to travel in the network. Let's say in WhatsApp you can send small files. It's very good. What if you try to send some 1 GB of file? It might fail, right? Most of the times it will fail. It won't. WhatsApp allow you to send that file, but mostly it will get failed due to some network issue or something. Right? You will have the performance issues. Right? Processing takes time as the data is processed by single unit, which becomes a bottleneck. Right? There is only one single unit that needs to process. Okay, let's say when you went to SBI bank, right? There are only one counter, and there are 100 users who want to deposit money. That's a bottleneck, right? Like you will wait, you need to wait so much amount of time. What if 100 becomes 1,000? The queue will go to the next village as well, right? That's what bottleneck is all about. There is only one person who needs to take the deposit amount, but there are many thousand amounts of people who need to deposit the amount, right? That's a bottleneck. In that way, you need, if you have the 3 or 4 counters for deposit, then it's a bit easy, right? That's what this traditional systems used to do. And master node get overburdened and may fail. Again, it's the same. There is only one deposit counter. The person who is taking the deposit, right, he will sometime he will get overburdened, and he may start entering incorrect numbers. You deposited 1,000 rupees, maybe he entered only 100 rupees, something. Those kind of things happen, right? But in real time also, this master node can get overburdened and may fail due to that monitor, memory issue, all those kind of stuff, CPUs, RAM, all those things. Okay, so for clear, what was the issue with the traditional system? Now, MapReduce allows us to overcome the above issues by bringing the processing unit to the data. Think, what if this person who wanted to take the deposit will come to your house and take the deposit? That's a good idea, right? You don't need to go to bank. You just book the thing, right? Nowadays we are booking many services. Let's think in future the bank will also send people to us so that they will take deposit amount from amount from us. Okay, but we need to have if that person free away with that money, that's the issue. That think in that way. Okay, what if that? It's very cost effective. You don't need to go to that. You don't need to go to that processing unit to process the data. Right? They will come to us and they will process the data, right? And the processing time is reduced as all the nodes are working with their part of the data in parallel, right? Small parts of data, these data nodes, right? These are the data nodes, 1 2 3 data nodes. These three different missions are working small part of the data. So that's why it's very easy for you. Let's say if you think, like, if I give these 3 votes for you to calculate how many number of votes here, it's very easy task for you. Okay, let's say there are only 100 words. I just give it to you. Okay, just calculate how frequency of this words in this 100 words. It's very easy task. But if I give entire task to you, then it's a burden, right? It's a very easy task. Now every node adds a part of data to process, and therefore no chance of a node getting overburdened. See, no one will get overburdened because we are doing the split logically, and this name node has some ethics. It will never do this split illogically. It will consider the load, and it will split the load as per its standards we set, right? 128 MB the block size. Okay, that's how it's split. Okay, fine. Still here, so clear, right? According to the advantage of MapReduce. If someone asks, you don't need to tell all this blah blah blah. Just tell them advantage of map reducing is parallel processing, data locality, and you can in the data locality you can say this processing unit will go and process where the data lies. Okay, but in traditional systems it used to happen like that. The data used to go to that container belt, right? It used to go to that processing unit and get processed, then it used to come back, right? Again the next one will go, something like that. But in the MapReduce, right, it doesn't happen. That the program will come to where the data lies, right? It will come and process the data, right? It's kind of barber coming to your home doorstep and just doing the whatever cutting or something, yeah, right. Now this is the traditional approach. Okay, this is the master, this is the slave, and this is, let's say, the data is sent from here to here just to process it. Okay, and in this traditional system, this data, this program, right, this program is sent to here and process it. You see this circle, right, this small circle, if you see here, that is a processing unit, and these are the data. You see this circle went to this data and processor it. This circle went to this data and processor it, like that, processing unit. Okay. Now this word count problem. You are already aware of this word count problem. I do not need to teach what is this word count problem. Number of words, and we need to calculate their frequency. Right. First, this is the input. Okay, and we need to split it. You know how we are splitting it, right? We are splitting in the river. Okay, RAV here goes into one split. We will never split it like this libraries will never split it like RA into one word, one split, and VER into one split. It will never do that. It will do logical splitting, right? This D beer river into one split, two splits, sorry, three splits. Now the mapping happens here. Mapping. Okay, mapping. Deer one, beer one, river one. Car one, river one, deer one, car one, beer one. Right? This is how mappings happen. You just, this is the key for you for now, as you not want to do frequency of the words, and this is the value here, key value pair. Okay. Now this will go into the shuffling. See, if you need to process this data, there are let's see what are the unique keywords. Let's start with this. Deer is the one keyword, beer is second keyword, river is third keyword, and car is fourth keyword. River we already counted, deer we already counted, car already counted, beer. There are four keywords. Four keywords. You see, beer, car, deer, and river. Right. That means this needs to go into like we need to make sure that all this deer will go into one place, and beer will go into one place. Maybe it's in the same place. Again, the beer can come and beer is here, and deer can also come and sit here. But we just wanted to make sure that all deer related data is in one place. Okay, and this beer will go here, river will go here. See, if you observe clearly, beer went into one, car went into one, deer went into one, and river went into one. It's simple, right, to represent, right? How this went? Using this shuffle sorting. Shuffle sorting. You know what is shuffle sorting? Shuffle sorting will make sure that the related data will coincide in one place. Okay. Now reducing will happen. How reducing will happen? Reducing will combine the data. BF2, car3, DF2, river3, and this is the final result. Any doubts here so far? Any doubts?
Yes.
No? You're
No,
clear.
sir.
No, no.
This is a famous problem, okay? Word count process is a famous problem. Maybe you will get this question in the interview as well. Just go through this after this class. Just go through this again and just try to understand things. Okay. Now, what is map reduced data flow? Now, let's see. This is the technical part. Now, for now, I just explained you the high level view, but this is how internally it happens. Okay. Input data stored on HDFS. Okay. Fine. Now input format based on the input format only, because let's say here deer space beer space river, right? Based on this only I need to split. That means after space, that means each word, right? After space, each word. Sometimes I won't have space, sometimes I will have comma, right? It's a kind of input split. Comma separated values, sometimes space separated values. Sometimes I could like someone is thinking very intelligently and they put some this mark, what we call it as at the rate mark here, deer at the rate, beer at the rate, river at the rate, right? It's based on the input split, input format type, right? That's a different format. Comma is a different format, space is a different format, those input formats. Okay, based on that we need to do input splits, right? What is input split? Input split is a logical partitioning of your data, right? You already know beer should go into as one word. Beer shouldn't go as be as one word, ar as one word, right? It should go as a single word. Okay, now the record reader will happen. Record reading, right? You will read the records, you will read these records, right? These records are read, no, these records are done. This is a single input, like this is a block that is sitting in your HDFS. Now we just read this record into three different splits. We just read that record. Okay. Now mapper will happen. How mapper will happen? We just saw this mapping key value pairs. You're constructing key value pairs. Now combining. Here it says combining. You already know input is a key value pair, right? You all, this key value pair. How you're calculating this key value? This is a key. This is a value. Key value pair. Okay. Now combiner. Mapper you just saw combiner. Now mapper will create a intermediate key value pair. Fine. Now combiner. What will happen combiner? That means let's say here deer river, right? If you go and see our example, this is a good example. So this is a mapping, okay, and this is a combiner, right? I just combined here itself, right? You see, good one, bad one, good two, bad one, right? Average one, good one, bad one, average one, good one, bad one, right? This is a mapper and this is a combiner. Okay, combiner. Actually, someone asked me why you are writing good one two times. You could have write good comma two times. No, this is mapping and this is mapper. Sorry, this is combiner. Okay, combiner. Fine. Now this is the where is this? Combiner. Done. Now partitioner. Partitioner. So this partitioner means in the how we are going to separate, right? We are needs to do this shuffle sorting. Okay, shuffle sorting, and we need to do the separations, right? How we will do is see. This is the shuffle sorting, right? Before doing shuffle sorting, we just see how is it partition or not. Like this program will just see is this partition, like it will just double check it's a partition or not. This is a separate partition for sure, right? This is also separate partition. This is a separate partition, right? Partitioner, and then this will go to the shuffle sorting and will go to this reduce phases. Partitioner, then go to shuffle sorting and will go to reducer phases. You see, reducer phases. Okay, reducer phases. Now this reducer will reduce the rate and give the output format. Output format. Reducer will take this. Okay, just take this. This is a reducer phase. Okay, and then it will give the output here. See, this shuffle short is doing all these things. Now from here it will go into output. This is the output. See, this is the output. Fine, output. Output, and output is stored in the HDFS. But here I am missing one more thing, that is here it is record reader, right? Here the before storing in the HDFS it is a record writer. I think I explained, it got explained here. Record writer, yeah. It writes these output key value pairs from the reducer phase to the output files. Okay, that's how it goes. Okay, nice. Now let's see in the simple terms what is input files. The data for a map reducer task is stored in input files, and input files typically lives in HDFS. Self-explanatory, right? Data is stored in HDFS. That is the input file for this map reduce program. Okay. So input format defines how these input files are split and read. Right? As I mentioned, depends on the comma, space, or at the rate, whatever you give. Based on that, this input split will get happen. Right? Let's say if that is you gave here deer space beer space river, then it should happen on the space basis, right? After space only I need to divide it into splits. Maybe I divide it here or here or here. It ups to me. But after that only I need to split. If you see here in an extra example, I gave comma here. See, bad after comma is there, average after comma is there. I'm doing in such a way that this after comma only I'm just splitting. If I do in between it's a illogical split. B cannot go into this and AD cannot go into it. We cannot separate a single word into two words. We cannot divide do that, right? We cannot do that, right? So that's what I'm doing. Based on the input files format only, I need to start splitting and reading. Okay, it selects the files or other objects that are used for input. It selects the files. What are the files, right? What are the input files it needs to select? Based on that, it will based on the input format, it will create the input splits. Okay, it is created by the input format. Cool. Logically represent the data which will be processed by an individual mapper. Logically, it never mentioned physically. Physically, we never do that separation. Okay, logically, one block is logically divided into multiple splits. For now, you can consider in that way. That will be easy for you. Okay. Now, one map task is created for each split. We already saw this. One map task is created for each split. Okay. Thus, the number of map task will be equal to number of input splits. Right? If one map task is divided into three inputs, okay, this one input is divided into three inputs, then you will have four map tasks. Okay. Now a question for you: if this input is divided into 1 2 3 4 5 6 7 8 9 10 input splits, then how many map tasks I will have? Hello. Hello. Yeah, I'll have 10 inputs. The input file, right? I split it into 10, 10 splits. Then how many map tasks I will have?
10,
How many?
10, right, sir?
10. Yes, 10 only. Why you are hesitating to say 10? Right? It's 10 only. You just saw here, right? It each there's input format will create the input split. Okay, that input split is in the map to individual mapper or individual data node, whatever we call processing node. Okay, then one map task created for each split, right? Each split will have one mapper task. That means in that way the number of mapper task will equal to number of input splits. Okay, now what if you have 20 input splits? How many mapper tasks you will have?
20.
How many?
20.
20.
2020.
20. Yeah. So that's how these input splits and mapper tasks are created. If someone comes and asks you in interview how many mapper tasks you will have, how can you decide that? You can say that based on the input split, number of input splits is equal to number of mapper tasks. Okay, you can just give this answer. See, this is highlighted. Mapper task will be equal to number of input splits. Perfect. Now, let's see what is record reader. You know, right? It communicates with the input split in Hadoop MapReduce and converts the data into key value pairs suitable for reading by the mapper. Right? Mapper needs a key value pair as an input. Right? Then this record reader will read that, will do that. Okay, do that and just create that key value pairs. Key value pairs you already know. Key comma one, that good comma one, good comma two, all those kind of stuff, right? That record reader will be created and it will be given to the mapper. Now it process each input record from record reader and generates new key value pair. Okay, and this key value pair generated by mapper is completely different from the input pair. It's true, right? Because if you see here, this is the key value pair. I mean, this is the original. If you see here, it's a bit different, right? Deer comma one, beer comma one, river comma. It never gave this, but we created this using this record reader and mapping. Right? Now, where are we? Yeah. The output of mapper is also known as intermediate output. Right? This is not the final output. This is the intermediate output, which is written in a local disk, written to the local disk. Okay. Just that intermediate written, right? It will be written into some temporary location in the local disk, temporary location, because it cannot put it into RAM. Spark will put it into RAM, but this intermediate result will be put into local disk ROM. Okay. Now the output of the mapper is not stored on the HDFS. See, it will never be stored in the HDFS storage, and this is a temporary data. And writing in HDFS data will create unnecessary copies, right? You do not. This intermediate data is temporary for you. You are working to get the final output. It's not the intermediate data you are working for, right? This will be stored in some temporary location. Okay, but let's say in hard disk, you will store it there, and then after some time, it will get deleted, automatically get deleted once this program is done. Okay, then it won't be stored in HDFS. Fine. Now the combiner is also known as mini reducer. Yesterday we saw this, right? There is this. See, this is the mini reducer. Good one, bad one, bad two. Good, bad one, good two. We just do the combining, local aggregation, local combination, combining, right? This is local combining. Here we have nothing to combine, so that's why we leave it as it is, right? This is reducer. For sure, after shuffle start, you will have a reducer, fine. But before shuffling, you have the combiner, mini reducer. You can refer to it. Okay, mini reducer. Now you have this mini reducer, combines mini reducer. Hadoop MapReduce combiner performs local aggregation. See, local aggregation on the mapper's output, which helps to minimize the data transfer between mapper and reducer. Right? Self-explanatory. You will go here, and if you see here, this is the mapping data mapper output. It will be gone to combiner, a mini reducer, and that will be this output is inputted to this reducer. Okay, reducer. Now, the partitioner. See what is partitioner. Let's see. Hadoop MapReduce. Hadoop MapReduce Partitioners comes into the picture if we are working on more than one reducer. See, if for one reducer, partitioner is not used. Okay, here in our case we are using two reducers. If you see here, we are using reducer 1, reducer 2. This is the final output we are displaying to the user. Here, these are the mapper tasks. This is the mapper 1, mapper 2, mapper 3, you can call it as. Okay, this is the reducer 1 and reducer 2. That means two partitions. I mean, two partitions we need to have. Okay. Partitioner takes the output from the combiners and performs partitioning. Okay. Partitioning of output takes place on the basis of the key and then sorted. We already know that, like based on the key will be get sorted, and by hash function key is used to derive the partition. Okay, I wanted to show you what is the hash function and how this will be done. Okay, um, let me open a notepad. Okay, hope so far fast is clear, right? If in case of any doubts or something, just let me know. Okay, hash function. Okay, okay, let's see. Let's go with 2. My hash function, how it will look is, let's say my key is 101, percentage 2. Do you know that this guy? Do you guys know this? This percentage 2 will give you the remainder. Do you know that? Yes or no?
Yes, sir.
Right? What is the remainder here? 101 by
One,
2. What is the remainder here?
one,
1. So perfect. 102 percentage 2. What is the remainder here?
two, sir.
2. I'm asking about remainder. Huh?
Zero, zero, zero.
Okay. So 103 percentage 2 will give, what is the output here? Anyone? This is very
Three,
simple mathematics actually.
three.
3. Why? See how this will look like is 2 divided 103. Here you will get some value. Let's say 51. Okay. 102.
One, sir.
1. This remainder will be 1. This is how your function looks like. Calculation division, right? Now, if I give that, I will, maybe you're not aware of this. Maybe in the program classes you should learn this. 103 by 2 will give me 51 as output. Okay, 103 percentile 2 will give me 1 as the output. Now you got to understand that 103 by 2 will give the quotient. Okay, 103 percentage 2 will give the remainder. Okay, understood now? Just
Yes,
remember this. These are very basic rules. Okay, you need to remember this. And if you will start practicing, I think it seems you never started practicing this Python and all, right? It's very basic mathematics in Python. Not even Python. It's very basic mathematics. You should remember this. Okay. Okay. Now let's continue. 103% of what is the output here?
one,
Reminder, please. Just refer here. What does percentage will give? No one. Just try. Just try. Attempt. Just try to say something. I'll walk you through. Hello.
Yes, sir. Yes.
Yeah. Yeah. Tell me. Tell me what is the value? Hello.
One,
Karthik, you want to say something?
one.
One. Fine. Maybe it seems very easy to you, that's why you're not speaking, or it seems very difficult for you, you're not speaking. Just let me know. Then we can put in a very simple, small example, something like that. Okay. Now 104% is 2. What's the output? Anusha, what's the
zero,
output here? 0.
zero.
107 percentage 2. What is the output here?
1.
1
1, right? Okay, you got to know what is the this function, right? Let's say this is the hash function. Okay, what happens here is, if this is the hash function, if this is what I'm doing, and what happens is all the values I'll have, how can I put it here? Let me create a box here. Okay, now this is one more box. Imagine these are two boxes. Okay, two boxes. So for all these one values, right, will come and sit here for the hash function 1. What happened here? Not this one. Okay, it will come and sit here. This 0, right, it will come and sit in different box. Hash function, this is what we call hash function 1. This is right, 0, 0. Okay, so now let's this 103, where this 103 will go and sit, let me know. In this one block or this 0 block? Hello?
1 block, sir.
1 block, fine. This again, this 104 will go and sit in which block?
0.
0, right, based on the remainder. Okay, that's how this partitioning is created, this hash function, right? What this hash function is, hash function will help you decide that where this row should go and sit. Okay, this partition, this hash function will help you do that. Similarly, that's what they are speaking here, hash function. Now let's say imagine let's say yesterday we discussed about good, right? Good, bad, ugly. Let's say for example, think it's not happen in the real time, but let's say if good percentage 2 gives me 0. Okay, it's not possible, but just think, bad percentage 2 double equal to 1. Now what is average percentage 2 double equal to 1. Now where this good will go and sit? Is it in 0 block or 1 block?
0.
0.
0. This both will go and sit into 1 block.
1.
That's how
Yes.
this hash function works. Hash functions will help you decide to shuffle your data. I mean, yesterday we saw this, right? This shuffling. It is this shuffling, right? How this shuffling happen is decided by this hash function. All the good values came here. Why? Because let's say this is 0. This block is 0. Okay, this block is 1. That's why you got values here. All like a good, right? Good percentage 2 is equal to 0. That means you got hit here. If good percentage 2 is here for this good value, it will be same for this good as well, right? That's why you got both the good values here. And similar, this bad percentage 2 double equal to 1, right? Then bad will go and sit into 1 block. Similarly, this bad will go and sit in 1 block. This bad will go and sit into 1 block. Similarly for average as well, right? That's how these blocks are divided. Okay, how shuffling sort happens, right? That's how it happens. Okay, now let's continue. According to the key value in MapReduce, each combiner output is partitioned. Okay, partitioned, and a record having the same key value goes into the same partition, and then each partition is sent to the reducer. Each partition is sent to the reducer. Okay, now this is how you see, right? Yesterday we decided, I told you that shuffle short will help you to do this. No, this is done by this what we call, this is done by partitioner. Partitioner will do that partitioning. It will take this data, it will put it here, it will take this data, good here data, put it here, average data, put it here, bad data, put it here. Like, it will divide, it will let you know how this function will work. Okay, now let's see what shuffling will do. Now the output is shuffled to the reduce node, which is normal slave node, but reduce phase will run here, as this is a reducer node. Okay, it's also normal node, but some reduce scripts are running here. The shuffle is the physical movement of the data, which is done over the network. Okay, as you already know, maybe you not know, shuffling means data is shuffling here and there. If you see the data shuffled right here and there, the data went here, like the shuffling. Shuffling means from one node data will go to another node, like data transfer between the nodes. Okay, let's say you guys used to share nodes, right? the nodes will go from one person to another person to another person, like shuffling happens. It needs to go through the network and reach your friend's WhatsApp, right? PDF file, right? Once all mappers are finished, and their output is shuffled on the reducer nodes, then the intermediate output is matched and sorted, which is then provided as input to the reducer phase, right? You already know this, how this input is given to the reducer phase. Before giving the reducer phase, you will do this, right? You will take this data, okay, this is mapper, you understood. This is combiner means mini reducer, right? That's why you got good 2 here. Otherwise, if this is not mini reducer, if it's not combiner, you will get good comma 1, good comma 1 still, right? But this is a combiner, that's why you got good comma 2, bad comma 1. Fine. Now this data should be partitioned in such a way that all the good values should go and sit into one partition, I mean one place, and bad value should go and sit into one place, and this average value should go and sit into one place. Okay. Then this shuffle sort will help you to sort the data in such a way that, right? Let's say in real example, let's put one more example. Okay. Good comma 1. Okay. Good comma 1, bad comma 1, bad comma 3, let's say. Then good comma 1, bad comma 1. Okay, this is how the data looks like now. Now what should sorting happens, how sorting should happens is this good, let's say B comes first, right? Let's say alphabetic wise, B comes first. It will take this here. Okay, B1. Now what is the next B value? This is the B value, right? It will take this B value and it will put here. Now B is sorted. Fine. Now let's go with G. G good value here. Okay. Now G here. Okay. Now G here. Okay. Now this is how the sorting happens. This is how the sorted data looks like. Okay. Sorted data. Let's see in one more case, it will go in like this. Bad 3, bad 1, bad 1, good 1, good 1, good 1. Okay. Let's go with good 2 here. See, this is how the sorted data looks like. Now it's clean, right? If you wanted to start calculating here, okay, let's take this. Let's put, okay, this is the entire data. Okay. Now let's start calculating it. How many goods are there? Good is 1 without sort. Okay, without sort. Okay, let's try to calculate without sort. How easy it will be, or with sort is easy. Let's see. Good is equal to 1, 1, and good is 1 more 1. That means good will be 2, and here good is 4. Sorry, 3. Right? You can just count with me. See, good is 4. Come on. You can just unmute yourself and you can just involve here, interact here.
6.
6. Okay. Good is 7. Okay. So good is 7 here.
6.
Okay. 6. Okay. Good is 6. Fine. Now bad. Bad is 1, 4. Again, I need to go here. 1, go here, because I need to scan. This is not bad. This is not bad. This is bad. That means I need to add this. So that means bad will become 1, 3, 1, 4, and here it is 5. Again, this is bad. That means 5 plus 3, 8. Okay, this is good. I just need to ignore this, and this
9.
some
9.
bad is equal to 9 something. Okay, fine. Okay. Now let's try to see shuffle values here. Okay. See, bad is 3, 3, 1. This is all bad, right? 3, 1, 1, 3, 1, 1. I just do this addition. Again, 2, 1, 1. Do this addition, right? It is very quick. So that's why it's try to sort the data. Okay. Sort the data. That's how the shuffling and sorting looks like. Okay. Now the reducer. Let's come to the reducer. Then the intermediate output is matched and sort, right? Which then provided into the reducer phase. Now it takes a set of intermediate key value pairs, okay, produced by the mappers as the input, and then runs a reducer function on each of them to generate the output. Now it's again self-explanatory. This is a sorted data. Sorted data. Okay, this is the sorted data, right? For sure, this is sorted data or unsorted data. Any doubts? Anyone have any doubts so far? Uh, this is sorted data or unsorted data?
Unsorted.
See this one.
First.
sorted data, right?
Sorted.
Yes.
Now this sorted data is given to reducer. Now reducer will apply reduce function. What is reduce function in our case? Counting, right? It will apply counting. Okay, counting on top of this, and we'll get the final output, that bad 9, good 4, something, some output. Okay, some output. That output of the reducer is the final output, which is stored in HDFS. Okay, it writes these output key value pairs from the record phase to the output files. And the way these output key value pairs are written in the output files by record writer is determined by the output format. Like whenever the user comes and asks us, gives the input, right? Let's say submit some input or something, then only the output will be decided by default. We will try to give it the same format. But if he wants us in some CSV file, Parquet or something, then we will give according to that format. Okay. Okay. So let's again try to revise this. Okay, there is one more concept called this yarn. Okay, maybe I couldn't cover this today. Let's try to see. You guys are okay for any tomorrow's call, Saturday call or something? Saturday same time evening or
Yeah,
something?
yes, sir.
Okay, I just want to hear from everyone. Right. Okay, no problem. I'll just try to put a poll in the group. Whether seems you go to work, right? So based on that, anytime is fine for me tomorrow. So I'll just put a poll in the group. Then you guys can decide. Okay.
Tomorrow
Okay.
evening, same time is fine. If
Hmm.
everybody are okay.
Okay.
Sunday I have exam, sir.
No, Sundays we will never schedule a call unless you guys ask us to have a call on separate topic. We just want to revise the topic. Then only we will have call. Otherwise, we will never have call on Sunday. Okay.
Okay.
Okay. Fine. Fine. Fine.
Yes, sir.
Okay. You guys can let me know. Yeah. Map reduce. Right. This is what we are discussing. Map reduce. Okay. You know the example, you already know how MapReduce works. You just don't worry about, because yesterday when I'm teaching this count problem, right, you're very active because this is a small example. But when it comes to the technical terms, there will be many things that you need to remember. So that's why maybe that's what you're lagging. But do not worry, that's why I always ask you to just go through this document before coming to the class. Then you will try to, like, when you first time encounter this word, right, then you will think, okay, what is this word? Maybe you couldn't understand that. That's okay, fine. But when you came to the class, when I tell you about that word, right, then it's very easy for you to understand those kinds of things. Okay. Now let's see again, what is input files. What is input files? Just let me know. Just everyone, you can unmute yourself. We are at the end of the class, right? You can just unmute yourself. What is input files? What is input files?
Data is stored in
Data is
HDFS.
stored in HFS, and we need to process that input file.
Yeah.
Okay. Okay, fine. Now what is input format? I gave you some good examples. What is input format?
After space only, it will split.
Hmm. Yeah,
Space,
but
comma.
yeah, I just gave that example for you. But in real time, input format could be CSV file, JSON file, Parquet file, Avro file, the file format. File format. Okay, real time. CSV means, maybe if you guys are not aware of this, seems like you're not aware of this. How CSV file look like is, CSV full form is, these are very small things actually, but you guys needs to start preparing. Okay, comma separated values. Okay, how this data looks like is Ravi, Arun, Karthik. See, sorry, it's space. This is how this comma separated value look like. Okay, these values are separated by comma. Okay, then Anusha, something. This separated by comma. That's it. Okay, now TSV files are there. TSV file means tab separated values. Okay, anyone aware of this thing? TSV? Anyone? No one? Fine, super. Yeah. Someone? Someone is aware of that? Fine, no problem. Okay. Tab separated value means Ravi tab, Arun tab, Karthik,
Sir, it is actually for the storing the tablet data, sir.
not tabular data, but when you receive the files, right? Like different sources will give different formats. Okay, this is
Okay.
not for the tabular data. We can say
Okay, sir.
um, tables. Right? You're speaking about tables or something like.
Yes, sir.
No, these are not tables. This is a file with a TSV file. Okay. Currently
Okay.
in market there are these two files, but I will create a new file for you, new format. Let's think in that way. Innovation. Okay. At the rate ASV. Now, at the rate file, at the rate separated values. Now, I want you to tell me, I'll take this CSV file, okay, put it here. My files are separated by at the rate. I mean, I just created this file. Actually, this is not there in the market. Okay, then what I will get here in place of comma?
At the rate.
At the rate. Perfect. At the rate. Okay, at the rate. See, you'll get these things here. Okay, at the rate. Now, I'll give you one more example. I think a DAT or something. DAT is supported by this one, I think. Yeah. Now tell me what I will get here in place of at the rate. You call
Line.
this,
That.
yeah, that, whatever you call it as. Even I forgot what is this is called. Okay, that one. Okay, this is what the file format looks like. Okay, CSV, TSV. If someone in future tells you what is CSV, don't get confused. These are the values that are separated by commas. TSV, that is separated by tabs. ASV separated by ASV is actually not a format. Okay, just ignore this. I just created that for your explanation. Okay, then that separated by these values. Okay, so these are the values. You just need to remember these kind of things. These small things, right? These are very small. This 1% to 1% one. These things, right? You just if you start practicing, right, you will get to know many of these things. They are small things. Maybe I thought like you guys are aware of that, but I will never know, right, unless we encounter that, right? Just try to start practicing, then you will get to know these many things, these small things. Okay, okay. Let's start. Let's continue. Okay. Input format. Now, input format. You know what are the input formats? What are different types of files? What is input format? The format of the file. Okay. So what are the input formats we have? Just let me know something. Even if it's wrong, no problem. Just speak it. Speak out. We just discussed what are input types we have. CSV file is the input format, right?
Yes.
TS,
JSON.
JSON is input format. TSV is input format. Okay, that is input format. I created a ASV format. Maybe no one will accept that, but I created a ASV format. Those are the input formats. Okay, based on that input format, this input splits are created. Input splits are created because it cannot follow very blindly, right? This job should be divided. This word should be divided by till here. After six characters, I will divide. After these characters, I will divide. No, it shouldn't be done like that. It should be divided based on the file type. This is comma separated values. That means it should be either break here or or it should break here, right? It should break here. And doesn't mean it should break in between. Like Karthik will divide into two parts. No, we will never do that. Okay, it based on the input file type format. It will divide. Similarly, here Arun as well. Karthik cannot again go like this, right? It either go here, divide here, or divide here. Okay, and that as well. It cannot happen in that way. So that's how input splits are created. Okay, and one map task is created for each split. That we already know, like how many maps we created. We created input splits, and that each input split is mapped to one mapper. Okay, that mapper number of if someone asks you map task, how many map tasks you'll have, you'll say that you'll say what? How many mapper tasks you will have in a map reduce function or map reduce program? How many mapper tasks you will have? Come on, you have the answer in front of you. Yeah,
Number of
number of
inputs.
inputs. Yeah, number of input split is equal to number of mapper tasks. Cool. Okay. Now record reader. Record reader means it communicates with the input split. in Hadoop MapReduce and converts the data into key value pairs suitable for reading by the mapper. You already know this example, right? This is the reader. Record reader. Record reader will create a key value pairs that will be given to the mapper phase. I mean next phase as we can call it as. Okay. It communicates with input split. It communicates with input split and create in Hadoop converts the data into key value pairs for reading the mapper. Fine. Now mapper, what mapper will do? It process each input record, each key we can call this each key and generates new key value pair, and this key value pair generated by the mapper is completely different. Okay. Let me maybe you started confusing here. Let me put it here this way that hmm, let me do some magic here. Okay. Hmm. Okay. Okay. Now here, how it will look is, here I have good, good, bad, right? How this can look like is good, okay? Key value pair. I'm not yet creating it. Again, good, okay? Sorry, it's a key, okay? And again, bad, I think, bad, like that. And here I will give the assign the value. Here I will give the assign the value. But here it might look like this: good, 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 bad. It's a key value pair here for now. But maybe I do not have anything here. Okay, I do not have anything here. You might think, okay, where is the value? No, let's think in this way. Like this good is created, then here this map reduce mapper function will create this thing. Will map some values to this. Here I'm just giving the keys, only keys. Okay, I'm just creating only keys. What are the keys here? This bad and goods are the keys, right? I'm just creating the keys here. Keys. Now this mapper is assigning value to these keys. Okay, what mapper is doing here? Mapper is assigning values to the key. Generates a new key value pair. Okay, and this key value pair generated by mapper is completely different from the input pair. Okay, we just saw this. This is a different, right? This good one, good comma one, and this is only good. This is only key. This is key comma value. Right? Now this is different. Okay. The output of mapper is also known as intermediate output, which is written to local disk. We already know this. This intermediate output is saved in the temporary, so that it will be removed after the entire function is completed, entire program is completed. The output of the mapper is not stored on the HDFS, as is the temporary data, and writing an HDFS will create unnecessary copies. Right? Self-explanatory. This one. The combiner. You already know. It's a mini reducer. It will reduce the out. It will perform some local aggregation and gives the output. That output is transferred to the reducer. Okay. Now partitioner. What partitioner will do? Partitioner will do some hash function, and it will take the data from one place to it will put into one block. We just saw that here, right? See, we just saw this blocks, block 1, block 0. We had two reducers. If there is only one reducer, then there will be no partitioning. All this data will go and sit in one place. But you have two reducers. That means this will go into one block, and this will go into one reducer block. This will go into one reducer block. Okay, two different reducers. Fine, two different reducers. This partition will help you. And shuffling and sorting. The output is shuffled to the reducer node. Okay, and the shuffling is the physical movement of data because the data needs to transfer, right? The data needs to transfer, and once all the mappers are finished, maybe I need to put it in this way. Okay, before shuffling, right? Before shuffling, what I will do here is um, okay, I will tell this, hey, you key value pair go and sit into one block, you go and sit into 0 block, sorry, second block. Okay, for now let's just go with second block, and this I will put. Okay, this go and sit in which block? Which block? Let me know. Bad will go and sit in which block? Which partition? Which reducer block? Whatever we call. Which block? You can observe this. This is 1, this is 2. Maybe this is confusing. 1. Okay. Yeah, just let me know where this bad will go and sit now. Hello. Hello.
Yes, yes, sir. Yes, sir.
Where this bad will go and sit?
Yes, maybe.
Yeah. So this will go and sit into second block. See, if you, this is where it should go, right? This MapReduce automatically creates some hash function. This name nodes and all, right? While this partitioning happening, it will create some hash function. This is the hash value, hash output we can call it as. Based on this hash output, these jobs are being let's see. Let me do it this way. Okay. So based on this hash value only, this will happen. Okay. Okay. Now this is done. Okay. Then the partitions happen. Okay. Partitions happen based on the hash value. I'll put some hash value here. Okay. Hash function. So based on this hash function, all this data is being passed to this hash function only. Okay. Just this hash function. Okay. This hash function, and based on that, it get shuffled. Okay. This hash function and shuffle are already part of the same. Okay, these are part of same thing. Okay, now this hash function will take this, will sort this, shuffle this, and put it here in the reducer 1, reducer 2. Okay, then the output is created. Okay, now the reducer will take this intermediate key value pairs produced by the mappers as the input, and then runs the reducer functions. Reducer function, you already know, right? How reducer function will happen? It needs to combine the results. Okay, then the record writer will write this output into the output files, and output files format is already decided. I mean, if they ask for the output, we will give it. Otherwise, we'll give it the default output. Okay, that's it. Now just see, this is the last one. I will just after that we can wrap up. Okay, definition. This is input split. Okay, this is block. Okay, what is input split? Input split is a logical division of data in Hadoop. We already discussed, right? When this data is being divided, we just discussed beer cannot go into be and air, right? We cannot, it can never happen. Input split is a logical division of data in Hadoop, and each map task processes a single input. We already know each map task will be processed by each input split will be processed by a mapper task, single mapper task. But block is a physical division in data in Hadoop. The block size is 128 MB in Hadoop, and which can be configured as needed. I mean, this block size you can configure as you need. This you already know. Okay, the purpose of input split is to control the parallelism in the MapReduce job. Okay, number of tasks you wanted to create, number of splits you wanted to create. The number of map task is equal to number of input splits. You already know that. The purpose of block is to optimize disk read performance. Data within a block can be read in a single disk seek. Okay, inside the block you can just go and read the data, and that data can be divided into that data can be used for like optimizing your disk and read performance. If you want to read that data, you will go and get that block, right? If let's say we saw a client will come and ask you just give me this output, then it will give you the address of that block, then it will go and get that data from that block, right? So block will help you to the optimize disk performance, read disk performance. Okay, that means like data within a block can be read in a single disk space, and I mean at once you can just read the data. Okay, dependency. Input split depends on the input format used in the MapReduce job. You already know this, right? Based on the comma files, CSV files, or TSV files, based on that, the input split depends. Input splitting depends. Based on comma, I need to divide, or based on upgrade, I need to divide, based on mod, I need to divide, all these things, right? The block size is a configuration parameter in the Hadoop system, and it's not dependent on the MapReduce job, right? This configuration 128 MB, we already decided it yesterday. All the developers sit together and just decided that block size of a Hadoop HDFS file is HDFS block is 128 MB. We discussed yesterday, day before yesterday, I think, right? That 128 MB. That is a block size is a configuration parameter in Hadoop system. It is not dependent on MapReduce job. Okay, the location. Input split can cross the boundaries of blocks, but Hadoop tries to keep them within a single block where possible for data locality optimization. Okay, so blocks are distributed across the storage in the Hadoop cluster. Like the Hadoop cluster, these blocks can go and sit anywhere. But input splits will also can go and sit anywhere. But here it's a logical split. Okay, it will try to cross the boundaries of blocks, but Hadoop tries to keep them within a single block. Okay, I mean in the single block, let's say you have 2 to 3 input splits. Okay, let's say this is a single block. Single block. Where is this? Single block. It has 1, 2, 3 splits. But if it tries to go into create one more split, it will try to do that. But Hadoop will never try to do that. It will try to keep it into single block. Okay, it won't. This input split can cross the boundaries of blocks, but Hadoop tries to keep them within a single block wherever possible for data locality optimization. Okay, Mostly these are very self-explanatory. Okay, you can just go through these documents. I'm pretty sure that here today you learned most of the things, new technologies, new terminologies, right? You can just start these things, start learning these things. Okay, then it will be very easy for you. Okay, so till here I will reset today's class. Okay, you can start. You can start asking doubts if you have anything. Tomorrow we will cover this yarn part. That's it. Okay, this architecture you already know. Before 2012, this is how architecture look like. After this is this look like. Okay, here you have Spark. Yesterday we discussed it. Instead of MapReduce, we can use Spark as well. But coming classes, you will understand all these things. Okay, users could write MapReduce program using scripting language. Users could write on multiple processing models in addition to MapReduce. The multiple processing models, Spark, Storm, you will get to know in future. Okay, tomorrow, I mean, if okay, we will start tomorrow's class and same time or something, and we will start discussing on this yarn. We will try to complete yarn by now. Then we can start other concepts. Okay, that's it. In case of any doubts or something, just let me know. How's the class today? Definitely, you had many new terms, and definitely, I'm pretty sure if it's easy, everyone will come and join data engineering. Okay, it will be difficult, so that's where you need to start preparing. Okay, so never think data engineering will be easy. There will be hops. You need to come out with. Okay, this is when I learned this concept in the first instance, right? It is very difficult to me, but I need to give some 3 or 4 tries on that concept. Then I got this concept. Okay, similarly, just go sit over the weekend or something. Just try to learn this concept again and again. Then you
Yes, Ravi, you are right because they need to go through this concept again and again. Otherwise, it will be very difficult for them to remember. Am I audible?
yeah, you're audible. Yeah, well said, Sushri. They
Yes,
need to go
yes,
through
yes.
these things.
So please means prepare in weekends. So as many as times you want to go through, just go through it. Also search in the YouTube videos also and try to understand the concepts properly because this is very, very important. So Ravi, are you uploading all these documents in the LMS? Okay, okay, okay. So you people are okay for the tomorrow's class?
Tomorrow, do we have a class like every Saturday? I just want to ask.
Hello.
Hello?
Yes, ma'am.
Yes, ma'am.
Yes, yes. So, as Ravi was telling, so we can conduct a class on tomorrow. So, if people are okay, then we can continue. Otherwise, we can continue on Monday.
Yeah, it's up to you.
Yes.
Yes, ma'am. We are okay with it. I am okay with it.
Fine. Tomorrow, let's try to put it bit early. Okay.
So,
Maybe 7 or
you
something.
tell
I'll.
me
Hmm.
because Karthik, Deepti, and the Diksha, I think Arun is not there. Arun, are you okay for tomorrow's class? Arun, are you there?
I mean, you can just let me know in the group. Actually, I have a call. I need to jump. So thank you. Thanks for the call. Just let
Thank
me
you,
know
Ravi.
you're
Thank
okay.
you, Ravi, very much.
So
We'll ping you in the group, sir.
yeah, thank you.
Thank
Thank you
you.
so much.
Thank you.
Thank
Okay.
you, everyone.
Thank you
Okay,
very
thank
much.
you.